Okay, so we're going to continue on in Module 6. So the last time we were together, we talked about belts. Today, we're going to be talking about chain drives. So I'm going to open up our Chapter 11 PowerPoint presentation. I'm going to kind of fast forward through the belt information. And we are going to be here on slide 16 that starts the section in our book, which actually is going to be on page 308. And this is going to be specifically getting us introduced to chains. Okay. So as we look at chains, chain drives, so we've already covered, I mean, this kind of rounds out the three main types of drives that we're going to be seeing in an industrial commercial atmosphere. And we've already talked about gear drives. Okay. We then moved on to belts, and now the last one is going to be chains. Okay. As we saw between belts and gears, there was a lot of similarities, just as far as some of even the terminology like pitch diameter, number of teeth, the purpose of the drive. And we're going to see those similarities here in the chain section. So first and foremost, the function of the chain in a chain drive is to transmit rotational motion and torque from one shaft to another, okay, in a smooth, quiet, and inexpensive way. Okay. Chain drives, I like to think of, they're kind of like a combination between both belts and gears. Okay. So what's kind of nice about chains, if we go underneath, I'm certain that all of you are very familiar with, like a chain link. Probably most popular would be, the mechanism to drive a bicycle, right? And they're used in other places as well. Probably if you look up in your garage and you have an automatic garage door opener, you're seeing chains, help with that process as well. But so the chain itself is there. It fits over the top of these teeth on what we're going to be referring to as the sprocket. So this is where this is kind of like a gear, all right? The teeth are going to be a different profile, of course, to fit between the chains. But this kind of has some of those properties of that kind of looks like a gear, okay? And then as we look at the chain going over those sprockets, you'll notice that now it kind of looks more similar to that belt drive where we have that opportunity to change that center distance more readily. And then also you can just kind of see how it rides over the top. So, like I said, I think this is kind of a nice, combo package, if you would, between a belt and a gear drive. Now, chains are very low cost. They're very low cost, and especially in an industrial setting, because they're just made out of, basic metal and steel. Okay, so very readily available. And because of that, they're very popular. They're mass produced, and we're going to find out that there are standards, associated with chain sizes. So all of a sudden now you've got standardization and the cost comes down considerably. Chains also offer us that ability to not slip like belts do. Now, that can be a positive, especially when we're trying to transmit higher forces and torques at lower speeds, okay? But it can also, hinder us where we can end up maybe damaging more machine elements because we don't let go, if you would, okay? It says here that we provide a more efficient power transmission. So in that sense, what that does is because it doesn't slip, we get kind of like, all of the horsepower, going, right through and being able to use most all of it. It also has that flexible center distance option. As I said earlier, with gears, we're locked into the size of the gears and where their center distance is going to be. When we have belts and chains, we can move those center distances and be able to adjust those to maybe, customize exactly what we're trying to achieve. Additionally, because of the arrangement, just like with belts, whatever the rotational direction is on our input shaft, it's going to be the same direction on our output shaft because we don't have them interacting with one another directly. Gears, as we know, we switch directions on our input to output when we have two gears in combination, but on belts and chains, that direction of the rotation is consistent between the input and the output, or the driver and the driven. It's more effective than belts at lower speeds, as we said earlier. Most often, when we have applications that are lower speeds, they're going to be applications that require higher transmission, or a transmission of higher forces or larger forces. So chains just do a better job of that, because belts, just by their nature, are probably gonna slip sooner than what belts are. Or I'm sorry, chains are. They also have very little maintenance, but they're not maintenance free. So for instance, we have to add some lubrication onto them. So whether it's greasing once in a while, or especially when they're higher speeds and they're used long term, more of like a continuous duty, as we would call it, then we're going to be building in lubrication systems that actually keep lubrication on there. As you can imagine, because it's metal on metal between the actual chain itself and the sprocket teeth, heat can build up, especially when we're at those higher speeds and using them over longer lives. And we also have longer service life with belts. Again, just the nature of using metal, it's going to last longer as long as it's sized appropriately. Okay. So that's chains. Now, different types of chains. The most common is going to be the roller chain. And this is going to be the type of chains that we would see on like bicycles. Okay. But we have some other variations on that. So we can look at page 308, and we're going to see a couple different types of chain arrangements here. So the first one, as we said, this is just a standard roller chain, okay? And I say standard because this covers most all applications that we see. You'll notice that this is a single strand, okay? And it's got two side plates, and it's got a little pin going across, or most often referred to as the roller, okay? And that's why it's called a roller chain. All right. Then you're going to notice that we have them where we have multiple strands. So we can have, 2 strands, 3 strands, 4 strands. I think then it might skip up to 6 and such. And what's offered here is, when we have multiple strands, is that we can keep the profile of the chain lower, meaning the height of that roller chain. And then we can spread out the force carrying capability over multiple chains. Okay. As you can imagine, there's then a multiplier for how much force we can actually push through it. It's not a one-to-one, and we'll look at that a little bit later, but it does offer a little bit more strength without having to go up in chain sizes. The next one that we see here is, this is called an offset sidebar roller chain. This is for more heavier, chunkier, bigger applications. It has real high force and torque carrying capabilities, and it's usually meant for low speed applications. And then the last one that we have here, it's called a silent chain. These types of chains, if you ever, and I'm sure you have, ridden on an escalator, like, at a mall or places where they might be, maybe in an airport, you're going to notice that these types of chains are going to be used. Okay, kind of those slotted. We are going to focus, because again, this is going to be the largest application that we're going to see roller chains for, those industrial commercial applications. Now, chain pitch, right? We're going to start here with chain pitch. Now, this is again where it gets, I'm not going to say it's confusing, but you just kind of have to be aware of how they call out chain. So roller chain is going to be classified by its pitch. Now, it is going to be called out. We're going to say a number of a chain is going to be equal to its size. Okay, so for instance, if we're given number 20 chain, okay, that is going to then correspond to a size, all right? And it's going to be what we call the pitch. And if we look here, I'm going to go underneath, you're going to notice that the side plate of roller chain, and that's this right here, okay? It's one of the side plates pulled off, and I'm going to go back over here. It's one of these side plates right here. If you notice how this is connected, we kind of have these overlapping side plates, and they're going to be called they're called the side plates, and they're going to hold the pins together on the roller chain. Now, as we look, you'll notice that the center of the hole on that side plate is going to join to the next roller. that distance between the center lines on that side plate of the two holes that are going to line up with the rollers is going to be called the pitch, okay? We've talked about pitch before, where if we look at, for instance, on our gear teeth, if we look at what we call circular pitch, it's going to be the point on one tooth, the distance to the very same point on the next tooth. This is that same application. So the pitch is going to be how far apart are those two holes, okay? Now, like I said, when we specify chain or when we call chain out, we call it out with a number, all right? So if we go back to our PowerPoint presentation, you're going to notice here that the size that we call it out, or the number that we call it out with, in this case, is number 120 chain, okay? Number 120 chain has a pitch associated with it as far as what is the distance apart on those two pins. And what we do is we are going to divide whatever our pitch number is by 80, okay? And by dividing by 80, we get a value of 1.5 inches, okay? So if I go back over here, that would mean for a number 20 chain pitch, this distance between the two holes on our side plate, which is the distance from one roller to the next, is going to be 1.5 inches, okay? If we have, for instance, if we change that number and we say, oh, well, if it's number 60 chain, which is another popular one, we divide that by 80, that's going to be what? 60 divided by 80? It's going to be 3/4 of an inch, 0.75, right? So 0.75. So if I go back over here, that means it's going to be 0.75 distance between the two holes on our side plate, which is going to be the distance between each one of the center lines of the rollers on our chain, okay? So as you can imagine, the higher the number, the bigger the chain, okay, distance, or the pitch distance, which is going to be the bigger the chain, okay? And then it also says here, and the greater the power capacity, okay? Meaning that I can push more force and torque through those larger, chunkier chains. That's the intention, okay? Now, multi-strand chains, we saw a picture of that, but multi-strand chains can be used to increase that amount of power transmission through that chain drive, but they do not provide, in this case, a direct multiple of a single strand capacity. Meaning, if I have one and I know what the strength is, I can't, if I have two, I can't just multiply it by 2, all right? Instead, the multipliers are, as we see up here at the top of page 310 in table 4, or table 11.4. So here, the number of chain strands is going to be across the top. So if I look at 2, my multiplier factor is not 2, it's 1.7. And the reason for that, if we go back and we look at the picture here of the multi-strand, you're going to notice that they share the side plates from one to the next, okay? From one strand to the second strand. There's not an extra plate in there. There's only one plate between them. So that's why it's not a multiplier of exactly, 2 or exactly 3 and such. So we have to know what is our multiplier when we have multiples, okay? And you'll be using this for your for determining that. Oh, the other thing I want to point out here is you'll notice that we can do 2 strands, 3 strands, 4, 5, and 6, but then we skip and then they start going to like 8, 10. So you have to know per your manufacturer of your chain, what are the appropriate multiples? Because you can't just say, oh, I want 7 multiples. That's going to work for me. You have to have something that is available per the standard. Okay. All right. Sprockets. Okay. Sprockets are going to be the toothed wheel that connect to the shaft and they mate with the chain itself. It's what the chain rides on. Okay. So if we go back underneath here, a little bit further down on that page 310, this is a picture of a sprocket. Okay. Now the width of the teeth on the sprocket, which are around the perimeter here, this width is set by how far apart those side plates are. These teeth fit up in between each one of the spaces in the chain. So that tooth is going to fit up inside that space between the rollers on our chain. Okay, and I think that's obvious, right? So what that means is we have to make sure that whatever sprocket we pick is going to mate and be the same pitch as the chain that we specify. Okay, look down here. So the teeth on the sprocket are designed with geometry to conform to the chain, pin, and link. If we look at figure 1111, which we just did, you're also going to notice that not only does it have teeth, but a lot of times it has a hub. And all that does is it lengthens out the amount of distance that we're going to connect then to the shaft that we're going to be putting through there. Many times we're going to also have a key that's going to keep it at the same rotational speed of whatever shaft it's mounted to. So sometimes we want that longer so that we can get a longer key in there and design for that. The pitch diameter is the diameter across the middle of the sprocket teeth. So if we go back over here, you're going to notice that there, and I don't know if it's a great illustration or not, but the pitch, just like it was for gears, it's not the top of the tooth, it's not the root or the bottom of the valley of the tooth, but it's in between here. And this is going to be, just like it was for gears, that effective diameter where it's actually going to be transmitting the force and the rotational speed from the teeth here to the actual chain. Okay, so it's like in the middle-ish of that tooth. And that is going to be our pitch diameter called out with the variable lowercase d, just like it was for gears, actually. Okay. Now, if I look at the chain drive geometry, okay, that's going to be our figure over to the right here. What a chain drive consists of is going to be a driver sprocket. Most often that's going to be the higher speed shaft, which usually has the smaller sprocket on it. It's going to be a lower speed or a driven sprocket. And then it's going to have the chain going over the top of it. And then additional information is going to be, okay, how far apart are these going to be? And that's going to be our center distance. Okay. So to call out a complete chain drive, we're going to be calling out the chain, the two sprockets, and then specifying the center distance. And then additionally, how long is that chain going to be? Okay. Now, to specify a full drive, all right, the things that we have to specify are going to be, first of all, the pitch, okay? So the pitch is going to be determined by, on page 309, sorry, I'm going to make this a little larger. So on page 309 here, you're going to notice that we have this chart, okay? And this chart helps us to determine what is the number of the chain, or what is that pitch of the chain that we're going to use. Remember, the pitch of the chain is going to be the physical size between the rollers. The larger the pitch, the bigger, the chunkier the chain and the rollers that we're going to have, which means that we're going to have higher force and torque carrying capabilities. So where do we start, and how do we determine, what that size of that chain is going to be? It's going to be this chart right here. Now this chart, it says this is the chain pitch selection guide. You're going to notice along the bottom here, this said this is going to be the speed of the small sprocket in RPMs, okay? Small sprocket is normally going to be that higher speed, that driver sprocket, okay? This is where things are coming into our drive. So it's the input, if you would. So down here, we're going to find where our RPMs of that higher speed sprocket are going to be. Then what we're going to do is we're going to make our way over on the vertical axis. Notice that here they have a couple different columns, okay? The first column closest to the chart is going to be for one strand of roller chain. If you have 2, 3, or 4, then you would move over to the left. And you're going to notice just by looking at the top numbers, as you move to the left and you have more strands, you end up having, higher capabilities there. All right. Now, this is going to be your design horsepower. Okay. Now it says design horsepower on it, but we're going to find that as we do our examples, we're going to be given a horsepower coming off, for instance, in a motor or a gas engine that is driving our chain drive, and that is going to be whatever that horsepower is coming in is going to be the design horsepower. That horsepower can be affected by maybe some other factors or variables about the operation of that particular application. And those you're going to take into consideration when you're in machine design problems or machine design elements, where now you're going to be considering what is the input power, what is the output machine that you're going to be going to, and maybe some other things about the speed, and then also the life that you're going to be doing. But for the most part, design horsepower and horsepower in our problems are going to be the same. So once I find my horsepower along that vertical axis, now I'm just going to bring those two together, and wherever I land in a section is going to be the number that I pick. So each one of the numbers going up here is going to be standard roller chain number. Now, whenever we specify the size of roller chain, we're going to give it in this number. All right. So notice that it's an integer number, and there's only a select few numbers. So you've got number 25, 35, 40, 50, 60, 80, and so on as we go up. So we're going to specify a number of a chain, but then we're going to figure out its pitch. This number right here, the distance between the rollers and the centers of the holes on our side plate, that is going to be taking that number divided by 80. Okay. So pitch is going to be the physical numeric, the size, but the number of the roller chain is going to be the designation of it. Okay. So another thing that we have to specify is going to be the number of teeth on the sprockets. If we turn the page and we go to page 310, but at the bottom, we have table 11.5. These are the commercially available single strand sprockets. Okay. So if we look, here's going to be our chain size in that number. Okay. So if we look at, for instance, number 60 chain, if we go to the right, the number of teeth on the sprocket that are available, it says, okay, the smallest one that you can have is going to have 8 teeth, and it's going to be all the way through 60 teeth, meaning in 1 tooth increments, I can get a standard sprocket all the way up through 60 teeth. Okay, so I can get 8, 10, 15, 25, all the way to 60. And then notice that the numbers then become a little bit more specialized. Okay, so it skips to 62, then 63, 4, 5, 6, 7, 8, but then it skips 69 and so on. So each one of these is kind of gives us the guidelines of the standard number of teeth on a sprocket. Now, if you are buying, and which you will, you'll buy from a specific vendor, although these are good numbers based on the standards by the body that governs the chain industry, if you would. These are good numbers, but you would always want to use your specific vendor catalog to make sure that the number of teeth that you're specifying for your sprocket is appropriate or available. Pitch diameter, we already talked about. That's the pitch diameter of our sprocket, where the roller has its effective diameter and transmit the forces and the rotational speed. And then pitch, as we talked about earlier, is going to be determined by the that dividing by 80. Then if we look at center distance range is going to be 30 times the pitch. Okay, so when we calculate the pitch, all right, when we calculate the pitch, we are then going to multiply it by 30, and that's going to be the smallest center distance that we can have. We're going to multiply it by 50 to get the largest center distance that we can have. And so your center distance is going to be between those two. Now, just like we did for belts, we had that very same, type of an application where we needed to find the range. So you'll notice here that as we look at that center distance, we have the chain that's going to be going around. Now, something that's a little bit more unique about the chain drive than it is for the belt drive is because the chains are made out of metal, they have weight to them. So what ends up happening is they can sag on their own weight. And what we don't want to happen is for us to have too much slack in that chain. So that's why we have this appropriate range for the center line because we don't want it too far apart, but we also don't want it too close together. So this is going to be something that we're going to check for the center distance to kind of get us in the ballpark, but then also make sure that we're not exceeding that on our actual chain or our actual center distance. Then we can calculate the chain length. This is going to be equation 1111. So if we go underneath, you're going to notice that it's a pretty hefty equation. So it's right here, okay? And then the center distance, once we know what our given chain length is, we can compute that center distance here. Another pretty hefty equation that we're going to be working through that, consists of the number of teeth on each one of our sprockets. The last element that we have is going to be angle of contact. The angle of contact, I like to say, is going to be how much wrap do we get on here? Okay, what is the angle of the number of teeth on our sprocket that we actually have engaged when we're transmitting and rotating around on our sprocket? So we would get an angle of wrap on our driver, which is our input over here, and on our driven, which is on the opposite side. Now, you're going to notice the designations of the ones and the twos. These are consistent with what we did with belt drives, where the ones are the driver and the twos are going to be the driven. And really, that also equates to usually the higher speed is going to be our driver, the lower speed is going to be our driven. Okay. And then the equations or the equations to calculate those angles of contact are going to be what we see here. All right. So we'll be actively using these in the application of the example that we look at. So we'll kind of continue on here. So chain drive kinematics. So velocity ratio and chain speed. These two sound very familiar based on our gear experience and our belt experience. So velocity ratio, and this is really looking at, I'm going to go back to our drive illustration. How many times does this low speed pinion, the low speed sprocket, the driver, how many times does this go around in order to get the driven to go around one time, right? So we've calculated this for gear sets. We've calculated this for our belt drive in our previous portion of this module. And then now it's going to be the same thing here. So, So the velocity ratio is going to be calculated using equation 1115 at the top of page 311. And notice that we can use the angular velocity of the driver divided by the driven, or we can use the diameter, the pitch diameter of the driven divided by the driver, or we can count the number of teeth on our sprocket for our driven divided by the driver. Now, it is not a typo that our angular velocity, number one is on top, number two is on the bottom, but when we go to the physical sizes of the diameter and the number of teeth, that the two goes on top, okay? Remember, I like to think of it as the larger number is going to go on the top. When we're rotating around, the driven, okay, driven N is going to be faster. So that larger number is going to be on top. The two here, which is the driver, okay, that's going to be on the top when we have the physical sizes. And over here, we can see the driven side sprocket is physically larger, okay, and it's going to have more teeth. Okay, so that's why it shifts and it goes to the top in that case. The other equation that we see just below here, 1116, this is called the chain speed. This is VC. This is what is the linear speed? How fast is that chain going? If we go over here to our illustration, It is this straight line velocity as our sprocket is rotating around, either one of the sprockets, okay? Whether we're on the driver or the driven, that chain speed will be exactly the same. It's that linear velocity relationship for the rotating element, okay? We've also calculated this many times. So V sub C is going to be the radius of the sprocket, or the pitch diameter, divided by 2, multiplied by the angular velocity. Now, if I happen to be on the driver, notice that my D1 and my W1 are in the same. Okay, so I'm looking at that shaft. If I'm on the driven, then I use the pitch diameter of the larger sprocket times its speed. Okay, in both cases, just like it was for gears and belts, this W, this angular velocity, in and out of this equation to solve for straight line velocity is going to be in radians per second or radians per minute. Okay. As you know, problems are going to be given in RPMs. And if we're asked to find out, what is an output speed and angular velocity, then we need to report it in RPMs as well. But in and out of this equation, radians per second or radians per minute, whichever seems appropriate for the application. So those are those two equations, which we'll revisit again. Look at one more thing. So I thought there was a chart. Oh, it is over here. Okay. The other thing before we get into our example, I wanted to point out at the bottom of that same column, there is a little section here where it talks about lubrication for that chain. As we said earlier, they're low maintenance. Chain drives are low maintenance, but they're not maintenance free. So we have to think about, putting some sort of lubrication on there. And that's going to depend on what is the the chain speed that we end up calculating. So we're going to calculate that chain speed, and then we're going to classify it as low, moderate, or high with the ranges that we see here. Okay. You're going to notice here that for a low speed application, something below 650 feet per minute, that's what the FPM is, where you would do manual lubrication, where you would periodically maybe put some oil or grease on the links and you would just move along, kind of like our bicycles, right? Okay, every so often, every couple years, maybe even depending on how much you ride it, you're gonna just put a little lubrication on there. Okay. Moderate speed, anything that's between 650 and 1500 feet per minute. Now we've got to actually design in a bath lubrication, okay, where the lowest part of that gear gets a drip or a bath, or runs through a bath of oil as it's actually going around. Okay. And this just ensures, as you can imagine, the faster that chain is running, the more heat can build up, right? Because of the nature of those moving parts and them hitting each other. And then high speed, this is where you're going to actually incorporate a continuous stream on that chain of oil that is actually going to have a pump associated with it. So depending on where you're at here, and as the designer, you're going to have to take into consideration, do I also have to, number one, buy a lubrication system? And now I've got to actually design it into, what I'm designing for here and make room for it. Okay. So that's going to be something as well that you're going to be just specifying, not really designing in here, but just saying, hey, I'm a low speed application or a moderate or a high speed. So I'm going to have, the different types of lubrication. Okay. So let's do example 11.3 together. And what we're going to be doing is we're going to be determining an appropriate pitch for the chain, the number of teeth on the driven sprocket, the pitch diameter of both of the sprockets, and the chain speed. Okay, we're also going to indicate the number of links that we need for the application and what the center distance is going to be. So let's take a peek and let's read our application. So I guess I'm going to say in a nutshell, we're designing the full drive. Okay, so let's go underneath and look at the description of our problem here. Can I get it all in? I think I can. So it's at the very bottom of page 11.3. And if we look at the top of page 312, this is going to be a picture of our application. So let's go back and look what we got here. So it says we have a single strand roller chain is going to drive a 10 horsepower engine that goes to a lawn waste chipper shredder as shown in the figure we just looked at. As the engine operates at 1200 RPM, the shredding teeth should rotate at 240 RPMs. The drive sprocket has 18 teeth. Determine the appropriate pitch of the chain. That's going to be the number of the chain. The number of teeth on the driven sprocket, the pitch diameters of both sprockets, and then the chain speed. Also indicate the number of links in a suitable chain and specify the required center distance. Okay. So what I want you to do is, as we're getting started here, just like we've done for all of our problems, I want you to just kind of take a minute or two to identify the given information and line it up with what the appropriate variable will be, kind of as we have been seeing them in this chapter. Uh, I want you to just take a couple of minutes and then we'll compare just to be sure that we're all on the same page. But this is a good idea to just kind of organize the information that we're given here. So as we look at our problem, the given information here, now, although we don't use capital P as far as any equations. This is just the power that's being transmitted. We're going to find that when you go to machine design elements, you're going to notice that we specify it using capital P. All right. So even though we're not using it for equations or calculations here in kinematics, that's usually the variable that's given. So capital P is the power, and we only use it to determine what is the size of the chain that we're going to be picking. But then we're also given the rotational speed or the angular velocity of the driver, which is number 1, okay? And it told us that that was 1200 RPMs. The driven, the shredder side, okay, our machine needs to go at 240 RPMs. So when we look at our illustration, the smaller sprocket is going to be our W1, angular velocity 1, the driver, and then the driven is going to be the machine up here, the shredder, and that's going to be our W2. Okay, so 1200 RPMs down here, 240 up on top. Additionally, they told us that we're going to have 18 teeth on our small sprocket, on our driver sprocket. Okay, and just a little note here, 1 is equal to driver. I'm going to put capital R here, and 2 is equal to driven, capital N at the end. Okay. Okay. So first things first, we need to pick what is the appropriate size chain that we're going to use for this application. Okay. And so step number 1 is going to be chain size. Okay, chain size. And that's going to be in the form of a number. Okay, so that's going to be the first thing that we're going to be looking at. Now, if you recall, we're going to use figure 1110, which is back on page 309. It's this chart right here. And we're going to start by looking at the bottom. And the bottom is going to be the speed of the small sprocket. Okay, the speed of the small sprocket. So this is our input, our driver. And our driver is 1200 RPMs. Okay, 1200 RPMs. Now, if your number doesn't fall exactly on this chart or it's not mentioned, what I would suggest doing is doing an estimate if it's between, okay, or just going simply up to the next line. Okay, just to be conservative. The further to the right that you go, you'll have a bigger number, if you would. Okay. Then what we're going to do is on the vertical axis, this is what they call the design horsepower, but we were just given horsepower, which was 10. Okay, so we're going to go up to the line where there's 10. So all we want to do is we want to find where 1210 come together, and you're going to notice that it's in the zone of 40. Okay, 40. Now this is number 40 chain. Now, the placement of that, I personally would probably go to number 50 chain, okay? Only because it's close to going up, all right? If I was designing this, if I was out in industry and I was going to be putting my name on, I certify this, or this is what I'm going to design, I probably would go up to 50, only because it's kind of close to the line there, okay? I'd like to see it down here a little bit more, but the book stuck with 40, so we're just going to go with 40. All right. So in this example, you're going to notice that they chose the number 40 pitch chain. Okay. So it's going to be number 40 chain. All right. And that's from, was it table? No, it was figure 1110. Yes. 40, where does it say that? So if we go to that chart, you see how we landed in this section, and that's the number 40 section. Yeah. Now, the next thing we need to do is we need to determine, okay, what is the pitch? What is the size of that chain? Okay, that lowercase p. So lowercase p is going to be equal to the chain number divided by 80, okay? The chain number divided by 80. Now, unfortunately, units wise, this doesn't really come out for us, but we're just going to add inches at the end here, okay? So we know that we have number 40 chain, and we're going to divide it by 80. So our pitch, lowercase p, is going to be 0.5 inches, okay? And I really should put a box around this because that's something we have to determine. And then we also know that our number of a chain is going to be here too. So as we look, any questions about that? Always divide by 80 when we go from number to what is the size, the actual physical size. So we now can say that the chain is done and the pitch we have calculated. All right. I'm going to say chain size and dimension. So it's a number 40 chain and that pitch is 0.5. So I'm just going to go back one more time. If we look at the distance between the holes on the side plate, which is going to be the center of one roller to the next, as we look here, okay, that's going to be 1/2 inch between, right? The next thing we're going to do is we are going to determine, oops, I missed one. We need to determine the number of teeth on our driver. I'm sorry, driven. We know the number of teeth on our driver. We know it's 18, but we've got to find the number of teeth on our driven, right? So to do that, we are going to use the velocity ratio. So if we go back to page 311, the velocity ratio options that we have here are angular velocities of the driven to the driver and the pitch diameters as well as the number of teeth. So we're going to use the angular velocities and set them equal to the number of teeth here because we know what our driver is. We know what our driven speed is. We know the number of teeth in our driver, but we want to find our N2 here. Okay, so that'll be our only unknown. So this is going to be find N2. Okay, so we're going to say W1 divided by W2 is going to be equal to N2 divided by N1. Now, we need to solve for N2. That's our unknown because we know W1, W2, and N1, all right? So we're just going to simply multiply N1 up. So this is going to be N1 times W1 divided by W2 is going to be our N2. Okay, so just algebra. So now I'm going to say, all right, I have 18 teeth. I can keep these in RPMs because it's just a ratio here. So I can say 1200 RPMs divided by 240 RPMs. Okay, and that's going to equal our N2. So N2, what do we get? 90? And that would be RPMs cancel here, so that would be teeth. Okay. So that's one of the values they want us to determine, the number of teeth on the driven sprocket N2. So I'm going to scooch back up here. I now know what that is, right? Okay. Now that I know the number of teeth and I know my pitch, I can calculate my pitch diameters. That's the physical size over the diameter of each one of those sprockets. So pitch diameter here is going to be that distance from one side to the other from that over that effective diameter. So let me go over here. Okay. So step number 3, pitch diameters. Okay. Now the equations for these are found on page 311 as well. So here, this is the pitch diameter of a sprocket is going to be equal to, this is going to be the pitch in inches, okay, divided by the sine of 180 degrees divided by the number of teeth, okay? So we look over here, we're going to say, all right, D1, that's going to be of our driver, is going to be equal to the pitch divided by sine of 180 degrees divided by N1, okay? And again, that's equation, back over here, 1110. Okay. So if I go here, my pitch from step 1 is 0.5 inches, okay? 0.5 inches. So 0.5, okay, it's going to be equal to sine times 180 divided by the number of teeth on our small sprocket. So that's 18 teeth. So we're just going to put 18 there. Inches is what we want for our diameter. So again, here it gets just a little, it's really more about proportions than anything else. So D1 is going to be equal to 2.879 inches. That's going to be the pitch diameter of number 1. Make sure you can get that on your calculator. Okay. All right. And then D2 is going to be same pitch, okay, because it has to have, it's on their, the chain is common between them. But this time, this is going to be 180 degrees over 90 teeth, okay? Oopsie. 90, which is N2. So this is going to be 0.5 inches divided by sine times 180 divided by 90. Okay. So D2 should be 14.327 inches. Let's get the same thing. Okay. All right. So if we go back to what we need to find, this takes care of D1 and D2. All right. And just kind of revisiting our illustration here on page 310. So what we have right now is we have the pitch diameter of our driver, that's D1, pitch diameter of our driven, D2, the number of teeth on our driver, N1, the number of teeth on our driven, N2, okay? We also know the rotational speed of each, okay? So we're getting there. We're getting there. Okay. Going to kind of look at our example, kind of catch us up. So we have through step 3. So we just did our pitch diameters here, okay? The next thing they're going to have us do, because we're going to need it, is going to be calculating the chain speed, okay? Calculating the chain speed. Now, this isn't something they were asking us for, but we need it for calculations coming up and then also just checking to be sure it's within the range. So chain speed is going to be that VC, okay? The equation for VC is equation 1116 here. This is the straight line velocity component of the rotational speed of either one of those shafts. So it's how fast is that chain going, okay? So we need VC, okay? So we know that the chain speed is going to be equal to the diameter, the pitch diameter, divided by 2, because this is the radius, times the angular velocity, okay? Now, we can pick either the driver or the driven. Okay, but whichever one we do, we're going to use the diameter of that and its rotational speed. Okay, just because I don't know, I start with usually the faster one. I'm just going to do ones for each of these. You could do twos because we know both, and neither one of them is less calculated. So I know that the pitch diameter for D1 is 2.879 inches divided by 2, okay, multiplied by W1. Now, this is the equation where this has to be in radians per, and I'm going to see if they did minutes. They did per minute. Yeah. Okay. Oopsie. Said minute, and I wrote seconds. Minute. Okay, this is going to be radians per minute. It can be radians per second, just depending on the units that you anticipate. When we have belt speed and chain speed, most often they're specified in feet per minute. Okay, other things can be in, per second. So we're going to keep it in radians per minute. Okay, and that's going to be our W. So what I'm going to do is I'm going to do that conversion right here in the equation. So I know that my W1 was 1,200 revolutions per minute, right? So I'm going to do my conversion to radians per minute. So that means I have 1 revolution on the bottom because we need it to cancel, 2 pi radians, okay? And that gets it to, canceling out my revolutions, radians per minute, okay? So you don't have to do the 60 over or the 1 over 60 because we're going to keep it in radians per minute because we're going to eventually put it into feet per minute. Okay. So multiplying across the top, dividing by the bottom, our VC you get 10,853. I'm just going to leave it at that because it's a pretty big number. Now, the book, oh wait, 1,200, 2 pi radians. What did I get? Yeah, 1,200.
That's what I got. Yeah, I got that too.
Oh, I see. Yeah. So, and that's going to be in inches per minute, right? Inches per minute. Then we need to get this into feet per minute, okay? Because we'll find out that the answer here is in feet per minute. So we're just going to take and convert 12 inches on the bottom here is in 1 foot. Inches cancel, okay? So our chain speed is going to be 10,853 divided by 12. So 904.4 feet per minute. Okay. That's going to be how fast our belt is going, or I'm sorry, our chain is going. Okay. Now, if you look in the book, unfortunately, they kind of screwed up the numbers here. So if you're comparing, what they did was they converted their W1 first, okay? That should be 7539.6, not the 10,000, whatever number they have there. And then when you multiply this out, you get the 10,853. Sorry, I put a 7 instead of a 3. And then 904.4 feet per minute is the final answer. Okay. So just make sure you update if you're comparing back to what the book had. It's a typo. The numbers that they have for their variables are okay. It's just that the final answers aren't. Okay. Now we want to look, okay, how fast is this going so that we can determine what type of lubrication do we need to end up designing in. Okay, so this belt speed then, if we look back on page 311 at the bottom of that column, Our belt speed is 904, so it's going to be a moderate speed, which means we're going to have a bath lubrication, okay? So equals bath lubrication. And not that we're going to be designing in this case yet. This is the beginning of our design process, but we have to keep that in mind that based on this speed, we have to design that in, to our application. Okay. All right. Now we're ready to start looking at, we have our, if we look back over here, we have our chain specified, we have our diameter specified, we know what the number of teeth on our driven machine or driven sprocket is going to be. Now, all that we have left is going to be, and I should put VC, we have that done too. All we have to do is we have to determine the number of links for the length of our chain and the center distance, okay? Now, links. When we specify how long the chain is going to be, okay, and I'm going to put links here, we are going to find out that when we get industrial chain, it's going to be in bulk. If you've ever gone to like an Ace Hardware or a True Value and you need to replace chain, you go to the back of the store usually, and they have their chain on like spools. And what they'll do is instead of measuring, for instance, I need 2 feet of chain for whatever the size it is, they don't measure out the chain and cut it. What they do is they count the number of links that you need. Okay, so we're going to find out the length of that chain, and the length of that chain is going to be how long does that chain need to be to go over the top of both sprockets, okay? And we're going to actually specify it in how many links do we have to count off of our spool, okay? So that's going to be those units. Then the center distance, in this case, we don't have a dimension, okay? We don't have a dimension. They weren't like, okay, the distance between this center and this center is this many inches, okay? So what we're going to do is we're going to determine it based on the appropriate range, okay? And we're going to pick a number. The big book picks a number for us. If you're in that situation with any of your problems that you do, you just have to do that very same thing. Calculate the appropriate range, what is the minimum and the maximum center distance, and then pick a number in between. So in step number 5, that's what they're doing, okay? You're going to be like, well, why did they pick this center distance? Because it was just in the range, that's it. So the suggested center distance for a chain is going to be this equation right here. And this is found on page 311. This is the range for the minimum to the maximum, okay? So we're going to take 30 times the pitch, and then we're going to take 50 times the pitch. And between those two numbers is where we are going to pick our center distance, all right? Now, this is the pitch. Remember, the pitch is that distance between the centers of the holes in our side plate, or the distance between the centers of the rollers on the chain, okay? So we calculated that P to be a 1/2 inch, okay? So if you remember in step number 1, our P was a 1/2 inch. So, new piece here. So this is going to be step number 5. Okay. We need to say 30 times P is going to be less than our center. So our center is going to be in the middle, and then it can't be greater than 50 times P. So our center distance range is going to be 30 times 0.5 inches and 50 times 0.5 inches. Okay. So 30 times 0.5, I think that's going to be, is that 10 point? No, 15 inches. And our center distance then has to be larger than that, but smaller than 50 times 0.5. So that's going to be 25 inches, right? So somewhere between here is what our center distance is going to be. The book picked the mid-range, okay? They picked a mid-range value of 20 inches, okay? 20 inches. Now, this is just an estimate. This is a place to get started, just like with our belts, to determine what the length of our belt is going to, or our chain is going to be. We just have to kind of have, here's our estimate. So this is just kind of getting into the ballpark. If we were designing this, there's a pretty darn good chance that we kind of know what that distance has to be, right? Like I got to have it right about here. That's the center distance that we're going for. Okay. We're just picking it based on the range. Okay. Right now. Okay. So now step number 6 is how many links do we need for the length of our chain? So L, this is going to be length of chain, oopsie, in links. Okay. So not inches, but in links. And again, so that we can count them off the spool when we're at the hardware store or when we're, in the shop. So now the length, the equation for that, is right here. Okay. Now, don't worry about units for this. Okay. There's just kind of too much here. I wouldn't be able to fit them all in on my page, but know that your capital L is in links. That is going to be the final units. All right. So I'm going to write this equation in variable form first. All right. Just be careful not to, mess up the adding and the subtracting. So it's going to be 2 times C, which is center distance, divided by P, lowercase p, which is our pitch, plus N2 plus N1, which is the number of teeth on each of our sprockets, divided by 2, plus the pitch times, this time it's N2 minus N1, and you have to square that quantity, divided by 4 times pi squared times the center distance, okay? And I'm going to say the approximate center distance, okay? So now we're going to put our values in. And like I said, if I put all the units in here, I'm not going to have enough room. I would be on multiple lines. So just trust the final units. They're going to magically appear for us. So this is going to be 2 times our center distance. We picked, or the book picked 20, okay? Divided by 0.5, which is our pitch, okay? Plus our number of teeth in each one. So that was 90 plus 18. If you got to look back, feel free to do that. Divided by 2. Plus, okay, this is going to be our pitch, 0.5 times 90 minus 18, and you got to square that quantity before you multiply it by 0.5, divided by 4 times pi squared times our 20, which is our center distance, okay, from above here. All right. So we should get 137.28, but double check. I'm gonna put that in there. Pretty sure this is a good number. get 140.5.
I got 137.
Oh, you did? Okay, let me see. What did I do wrong?
137.2.
You did. 4, did I forget to do the have to find?
Do you have a Casio calculator?
No, I got an HP. I know I'm putting the numbers in. Okay. Did anybody else get that? Oh, I've got 2 messages. Maybe somebody. Same, you got the 137. Okay. All right. Yep. 137.28. So 137.3. Okay. All right. I'm just trying to. I've got it. 20s here. Yeah. Okay. I must be just putting in. I don't know. Okay. Now, this is links. So as we can see here, you would have to have an integer number. Agreed? Okay. So you'll notice that it comes out to 0.3. So we can't have 0.3 of a link. So you'll notice that the book is going to round up and their actual number of links is going to be 138 links. Okay. All right, that is going to be the number that they specify. So when we pull it off the spool, we're going to count 138 links, right? So if we look back over here, that means our L is done. Now that we have the actual number of links, okay? Remember the number of links here we specified based on a 20-inch center distance, pulling it out of the air, right? Like that should be good. But now what we want to do is we want to specify the actual center distance based on the 138 links, okay? Now, this one is a long equation, all right? Here too, want to at least do the practice, make sure we can get the numbers that are here. So the center distance is this equation right here. So really long. Here too, we're not going to put the units in. This center distance is going to end in inches. Okay, it will end in inches. So again, trust it. So I'm going to write it out first in variable form. So C is equal to, you're going to have that pitch divided by 4 times the number of links minus number of teeth in the driven plus the number of teeth in the driver divided by 2 plus, and then the square root of, there's a whole bunch of stuff underneath here, L minus L2 minus N2 minus N1 divided by 2. And then we're going to square that quantity minus eight times N2 minus N1 squared divided by 4 pi squared. There we go. And then this is our bracket around there. So you have to do all of this underneath here and then multiply by the pitch divided by 4. And that will be our actual, and I'm going to do actual center distance. Okay, and the number of links is what we decided on as 138. And our center distance should come out to be 20.187, which would make sense because it would be a little bit longer than the 20 that we specified when we calculated the number of links. Let's see if I can get this number. Actually, I'll put the numbers in. You guys get the 20.187? I know that's a correct number.
I screwed up.
It's, yeah, I try to do it in phases just to make it a little bit easier. Eight. You got it, Rainer? Awesome. Confirmed. Okay. And that's what's nice about kind of doing these example problems as well, especially when you get long equations like the last two here with the center distance and the number of lengths. It's good practice to just make sure that we get corresponding numbers. So the center distance here is a good number. So 20.18. If you don't get it the first time, then go back through and do it in chunks. And then don't forget to do the square root here. Then add, subtract. I kind of go backwards with mine, actually. But if you have a fancy calculator, we can put it all in. Maybe you can get it all in one line. I don't know. Okay. Any questions on this particular example? Okay. We didn't do an equation sheet for this. One thing I kind of liked, if you wanted to, you certainly could. But if we look at page 311, all of the equations are like right here. Okay. The only one that's not is when we have, oh, actually, is it there? I guess they don't have an equation for it, but they talk about how your chain pitch is always divided by 80. Okay. It's in the paragraph here and it was also in the PowerPoint. So P is always equal to whatever your chain number is divided by 80. Okay. But otherwise, all of those equations are on the same sheet. So I are in on the same page. So I didn't worry so much about creating an equation sheet, but you certainly can do that for yourself if you find that you want to put them all in the same place. Okay. So with that, if there aren't any questions, okay, then what I want to do is let's look at our assignment because that brings us to the end of our PowerPoint. Okay. So if we look at assignment number 6, okay, assignment number 6, the last problems here are going to be the problems pertaining to chains. So if we look at number 18, 20, 22, and 26. So the last 4 problems here are going to be our chain related questions. So this is going to be, these problems are going to be found at the end of the chapter, page 314. And you're going to notice that this is going to be in starting the chain kinematics section. So 1118, it says we have a gear motor operating clockwise at 220 RPM is coupled with a number 40 chain drive to a liquid agitator. The drive sprocket has 19 teeth, so that's going to be our N1, and the sprocket on the mixer, which will be driven N2, is 50. Okay, so these are number of teeth, 19 and 50. They want us to determine the speed of the driven sprocket. So the driver is up here. The driven would be W2. So that would be the output, if you would. And then this is the number of teeth on each. So you want to use that velocity ratio equation. And then they also want you to find the chain speed and then let them know what the recommended lubrication type is based on how fast VC is going. Okay. So that's that low, moderate, or high speed. The next one that you have here is going to be 1120. We have a shaft is on a gearbox is coupled through a number 100 chain drive, okay? Rotating a drive shaft. So this is going to be the driver of a pulp screen at a paper producing plant. The screen drive shaft operates at 250 RPMs clockwise. The drive sprocket has 25 teeth, and the sprocket on the mixer driven is going to be 76 teeth. Determine the speed of the drive sprocket and the chain speed. and the recommended, again, lubrication type. So this is going to be calculating for W1, the driver, and then you're going to find what the chain speed is. Okay. That'll be through that velocity ratio again. Then chain drive geometry. Here we have number 22, 2 sprockets for a number 80 chain, have 19 and 64 teeth. The chain has 140 links. Okay, that's going to be fitting over the top of those 2 sprockets. Determine the pitch diameter of each one of the sprockets, knowing the chain number and the number of teeth in each, what their center distance is based on the number of links here, and the angle of contact over the smaller sprocket. Also compare the center distance to the ideal range. So don't forget to do that last part. So angle of contact, we go back to our equations on page 311. Angle of contact is going to be this equation right here. That's going to be in degrees. And then once you calculate your center distance, make sure let the, like have a statement of whether it falls within the range calculated here based on the pitches of those side plates. Okay. And then the last problem that you have is actually just like example 3 that we just went through. And it says a chain drive is desired for a corn picker to couple a hydraulic motor with a drive shaft. The 30 horsepower motor will operate at 550 RPM, and the drive shaft must operate at or close to 100 RPMs. Select an appropriate chain size, commercially available sprockets, and the number of links for a chain. Okay. Also calculate the actual chain speed. That's going to be VC and the center distance. So just like the problem that we just did. Okay. You can use that as your guide. So that rounds out the items for module 6. Okay. Are there any questions on any of the problems that we see here? You're going to notice that there is a final answer key. Okay. Now, as we look at 22, and number 26, you do have some liberties in those problems. So the answers could vary. So it doesn't necessarily mean that there's one right answer. There's multiple right answers. Okay. So if we look, then that takes us to, if you would, kind of the end of our module 6. What I'm going to do is I'm going to stop our recording here.